So, hello everybody. Please let me know if you can hear me well and see me well, and you're ready to work. This will be quite intensive today. So yeah, let me double check if everyone is online. Let me know that you are here in the chat. And in a second, I will open a new template for us today. So we're going to work with real data set today. So today will be the first time we start working with proper data sets that like at least, so they'll be quite old data set, but still it was used for scientific research some years ago, and right now also useful for understanding things. So just a second, I will add the assignment 6.2. That will do together, because I remember some people wrote me on email that they are not comfortable of implementing the equations themselves. They still don't understand how to implement equations in Python, but that is something that is essential to the deep learning. So we'll try to implement equations that we constructed last time and achieve some results, and then move to the proper tasks then. So task 6.2 will be implement equations from 5th session. So that task is now alive. So the template 6.2, hopefully that's a proper template. So So just to clarify also, I didn't have the time to properly compile the best marks of the course yet, but we'll do that definitely next time. We'll hope that I will have enough time to properly go over your handed-in works. Those of you who resubmitted the works that you got zeros, I will evaluate those as well. No worries about that. So far, it seems like that Betty Rudzita is the best student in this course. She is from RTU. Then I think there is Armands is doing well. Then Gintz is doing well, except the last homework was not correct, but still he's doing well. So the Kristaps, both Kristaps, Bloomberg, Kristaps Siksna is doing well. So others are lagging behind. This is dangerous, because if you lag behind too much, you can get you might not pass this course. So that's something to consider. So today, hopefully, at least following up on the equations, you would be able to at least submit this work and get some points for this work, and hopefully then also previous homework as you would understand it better now. So okay. Okay, first things first, about do you have the access to the template? If somebody don't have access to the classroom or the template, please let me know in the chat. So you should have in your front 6.2 template. So do you have 6.2 template ready for work? Plus or Y. So if not ready, then Y. So maybe I have some problems there. Okay, so if there is some problems of running the Python Anaconda environments, you can also run that on the Google Colab on the online notebooks if for some reason you're not following. Again, I just want to emphasize that the purpose of this course is trying to get everybody as far as possible. It's not to fail people, but at the same time, like, if you don't put in the work, like, and actually submit those homeworks, I cannot really help. I really try my best in these sessions. So, okay, so we have the template here. We'll start coding just in a second. I will not show the like derivation of the two variables that were in the homework for the last time. Betty has submitted it correctly, very nicely. Others did not submit it from the yesterday yet, so you will do this later, but we will code it anyway. So the derivation would still be fine. Derivation would still be fine if you add it later, but basically, so yeah. Okay, so I will add in the Jamboard some of the equations that we're gonna implement, and you can try it yourself, of course, as well. I could ask it as a task, but unfortunately, I'm a little bit afraid that very few of you are able to implement very basic equations yet. Because I got that one email at least saying that person is not confident at all how to implement those in Python, so we'll do it together. So the model itself, the model looks like this. A linear layer looks like this, that's right. So I'm just copying from that previous slides few things. So, and we'll implement this now. So, okay, so we're having these equations here, and we have the same equations back in our Python, and that's quite easily done, I think, hopefully. So if you have so many questions or something with regards to those implementations or anything else, let me know. So we start with the linear layer. As again, I said, it's called affine or affine transformation or the linear layer or linear transformation. Or basically what it is the vector, it is the rotation vector plus translation. So just trying to emphasize that we did this many times. It should be quite confident about these equations. So now everything that we're doing is just like with single dimensional variables. By the way, at some point I will have also a question for you, because as you see in this template, I have the weights initialized as random variables in range from 0 to 1, but they are not initialized as 0. So maybe you have ideas why I did that. There is a logical explanation for that. So, okay, if you have, by the way, if you have any comments or whatever, you can write in the chat as well. So here we multiply it by the x and plus b. Of course, this could be a dot product as well, but it doesn't make sense to write here a dot product because the weight here, it is just like a single dimensional variable. And today, a little bit later, very soon, we'll start working with the dot products here, and we will combine basically, I think, at least 3 theories that we covered. We will combine the object-oriented programming, that will be very essential for these function graphs. Then we will combine the linear algebra of the dot products and the linear transformations of the vectors and matrices. And we will combine the calculus and partial derivatives. And that will create as a framework that would be able to, so that we could make really deep, really powerful neural networks. So, but right now we're yet at the baby steps, so this is just the quick implementation of what you had to do at least already 2 weeks ago. But yeah, thank you in the chat. I did not jump in the template, that's right. So if I do this again sometime, let me know in the chat. Thank you very much for that. So let me show you again what I was talking about. So we initialized I initialized weights and with a random variable. In this case, there is logical explanation for that. You can think of it a little bit later and write in the chat if you have ideas for that. Now I implemented the linear layer. So if you look carefully at the linear layer equation, so you can see this is a mirror image here. So if you don't know how to implement that equation, then look carefully and try to do this yourself. So then the next thing about the ReLU. So the relu is a conditional function. Again, multiple ways how to implement it. I will implement it using the Python Numpy syntax, probably. So, but you could try it, implement it with for loop as well, no problem here. So again, one thing that I must stress, even though here the weight is singular dimension, singular scalar value, the x is not, because the x is actually all of our samples together. So we are not looking at every sample step by like one by one, because otherwise the gradient would jump all around the place and we would probably not converge. So we're looking at all of them at once. So that means that actually the shape of the x here, shape is the so the 4 comma like that. So if the shape is like that, it is either we need a for loop to go over every sample in the x and do the relu function, or we can do some kind of quick numpy syntax. That's what I want to do now. So one is that I will copy the x. So what I mean by copying is that there is so if I just use the x itself, we would have the same problem with pointers. Nothing is copied automatically. So here with this MP array, I think it was the similar function with clone or something like that, or copy. Yeah, there is a copy function. So you can probably use also copy function or array. So that is the same thing. And it's serializing that memory and creating a new array. So if you not do that, then you would modify the x, and that is not what we want. So we copy all of our outputs, then we use the syntax of y, where this is lower than 0, we will replace it by 0. So this syntax, what it does, so let me show you, is if I call on array, so let me give you some examples. So if you have an array that is, let's say, something like 1 to -1 -2, and if I call now the y is under 0, it will produce a new array that contains of false, false, true, true, something like this. And this is a selector that you can apply to any existing array. That's why we use Numpy. Numpy is kind of similar to old times MATLAB things where we can just accelerate all of our vector maths. So now we just select all of our vectors depending on this condition and replace the value by 0. So and then we also need to return, of course, the y. Okay, so these are these things. So then we go to the model itself. So the model, again, very simple. Looking at the equation, if you don't follow these things, just go back to the slide number 2, look at the slide number 2 and think about it a little bit and then use it. So if I go to the slide number 2 and I see that we have at the outer layer, we have the linear. So this will be the linear. Sorry, so the outer layer is linear, then the outer layer parameters is W2, B2, then we have the relu, nonlinearity, relu, then in the nonlinearity inside we have another linear layer with weight 1, bias 1, and dx. And here again, try to emphasize this already yesterday, but that is the reason why we need a derivative with regards to x, because here, of course, derivative with regards to x in this part doesn't make sense at all. So, I mean, why should we change the input data, right? But in this case, it makes a lot of sense, because now, let's say we have some kind of inner x, so we can maybe split it out, so this will be some x hidden. So you can write it like that also. And now if you look at this equation, easily see that derivative with regards to x hidden is valuable, because that's how we get to the w1 and b1. If you don't have that derivative, everything falls apart. So hopefully this is clear so far. So I will I will just add maybe also the mean average error. I mean the mean absolute error. So the mean absolute error, again, very simple stuff. So that is just the NP mean. So that is average of with regards to any axis. So always the loss is just one scalar value. This is not a vector. So then ABS. So this is again fun thing. Basically, you can do the ABS with squared and I mean the square root and squared inside, like we did yesterday in our derivation. That will be the same function. So then y minus y prime, and we're done. So that's our loss function. So this will be our loss function. So let's do a few questions. So so far, well, just to check your understanding, do we include mean average error function in our production model after training? So do we include that function after training, plus minus? By the way, I will also quickly copy these functions in Jamboard as a code. So, of course, you will need to write it themselves, but still, just follow. So I have a question in the chat now. Okay, where is the? Oh, it's not copying. Should we include the mean absolute error? Mean absolute error function in our model when we train the model? So when after the training, when what is 200 epochs are finished, should we include the mean absolute error function in the production? Plus, minus? So Kristaps is saying we include it during the training. Yes, we do that during the training, but what about after training? Do we need it? Do we need it after training? Plus, minus? So Emil's saying that we don't need it after training. What others say? Okay, so it's very nice. Everybody is in consensus. That is correct. So you already learned something and understand something. That this is just a like proxy function for training. This is like generally not necessary for the actual production model. You could, of course, use it for inference for evaluating how good is your production model later, or maybe like depending on the loss function, it could be actually some kind of metric that is important later. But this is not part of the model. This is needed for calculating derivatives. Okay, so that's good. And also estimating the quality of the model during the training. Okay, so let me go back to the Jamboard, just a second. So I dropped in the code and explained some of the stuff so far. Okay, by the way, before we go further away, so is the equations and code clear so far? So far, plus, minus. And if minus, then what exactly is not clear so far? So, and I will start copying derivatives as well for the next slide. So let me find which ones we needed. Okay. we yesterday calculated 2 of 4 that we need. So we have 2 pluses confirming that you 3 pluses confirming that we understand. Let's see what our other thing. Meanwhile, in the third slide, and we'll start copying derivatives. So one derivative of the equations. That is from the loss function with regards to W2, and with regards to W1 as well. We need that one as well. So with regards to W1, that will be, so how could I just copy it out somehow? Okay, so I will like highlight it like that. So, okay, so now I have also with regards to W1. W1 is a little bit deeper, but still like nothing too complicated, like that. Okay, so we have those two ready, and I see that at least those who are engaging with the chat and hopefully would not lag behind with our tasks is saying that it's okay so far. So let's keep then implementing the second part of our task of derivatives so that we could learn anything. So okay, let's move back to the code. Okay, so we have those guys ready. Then we have the derivative with regards to x for the ReLU. Again, I will use the similar approach as before with this copying array, but in this case, the derivative is always either 1 or 0, if I remember correctly. Yeah, either 1 or 0. So that means that we can use NP1s like x. So the ones like x means following. Again, just assuming that maybe you're not that big experts on the Numpy yet. So let's see. So if we have some kind of something like, let's say, the previous vector, -2. So this would produce us just something like this. So there is also a function 0 or 1s like, and of course if you have 1s like, you can convert it to whatever, because you can multiply it, you can add something to it. Remember that in Python, in the Numpy, if I add Numpy array something, it would add to any element or multiply by any element. So basically, if we would like to have not something like this, but we could do for like something like this, for example, multiplied by 2, and this will just produce 2, 2, 2, 2. So that is why the Numpy is powerful. We can do all sorts of mathematical operations very easily. Okay, so we have this thing ready. Then we can use the same syntax as for the forward pass, just using a little bit different manner. So here we can have if the x is lower than 0, then this will be 0, and we return y. So that's great. This is done. Then let's see, we have derivative with regards to mean average, mean absolute error. So there is a bug in my text. It's m. So everywhere else it's correctly. There should be MAE, not MEA. So that's a typo. So anyways, here, like just to make a little, so that we don't lose the minus sign for the chain rule, I will add the minus sign in front. And here, let's say we have y minus y prim. So that's, let me check, did we add that derivative? I think I did not add derivative to the slide, so I will add that one as well. So okay, let's do step by step. So I will add the ReLU equation implemented in Python to the Jamboard, and then I will drop in the Jamboard from previous time, and also the equation for the mean absolute error derivative. So that was also calculated already quite successfully. Mean absolute error derivative. Okay, so it's a little, so it's actually here basically. Okay, let me, so I will somehow mark it. So if we go here just a second, I will go back. So the mean absolute error derivative is, so there is a minus sign, at least here in this part, this thing, well, it's not there, there should be a minus sign, so I will just add it. So I think here we should have minus sign, and basically this thing then is the derivative of the mean absolute error, the mean absolute error. So okay, so we can now implement that as well. Of course, we can just combine everything in those final equations as we did here, but to make it a little, so we don't repeat the stuff many times, it's better to implement them just like once and then use twice. So okay, this will be fine. I will go back to the code. Okay, so here we have this part, so this should be divided by the absolute value of np-abs of the same thing. So the order matters in sense that like if you calculate the derivative with the order where the y prime is first, then the minus sign will not be in front. So the minus sign is something that will count, if you do the chain rule, it will depend on which variable is in which place. So that is important aspect here. Okay, so that is here. Then derivative with regards to weight 2. That is something we also implemented already successfully. Derivative with, so again, because this is a mean, so we calculate the mean over all of the batch. So the batch is, in this case, we have those 4 samples. So we calculate the mean over this batch, and it will contain, so this will, the derivative with regards to weight 2. So the weight 2. Okay, so probably it would be nice also to pre-calculate y prime. By the way, that's also something that we'll do today, so that we don't need to pre-calculate always. We can pre-calculate just once. So this kind of structure of the code is not optimal at all, but hopefully it just tries to illustrate the logic. So y2, b2, and x, I think that's about it here. So you have the y prime calculated. Then we do the derivative of the y prime mean average error, and we use the y and y prime here, and then we multiply it by the rest of the equation. So the rest of the equation we can just copy probably from here up here. Again, not optimal, so if you would not have this one, then it would be even more not optimal. So anyways, we just copied this one. This is clear. So then the second one, for the derivative of weight 1, so we can copy all of this thing, and it will be a little bit more. So we have y prime, and let's call the second part of the equation so that it would be not too long. So here there is this ReLU stuff that will come off, and instead there will be the y2, and then then there will be d ReLU, dx ReLU. So with regards to the x, and this will be as before this inner part, so pre-calculated inner part, and multiplied by x. So that is that equation. So that's great. So these two equations are good to go. So then there are two equations that you had to do at home. So I will not show the derivation of those equations, but I will implement them together here, and you will later then show me the way how you calculate the derivation for those equations in your homework from previous time. So I drop these into Jamboard in the slide 3. Okay, that's good. So then let's look at the next part in these things. So these things actually, like, visually do not change a lot from what we have. Like, it's actually more easy. It's easier than those those derivatives that we already have. So here we can just copy the thing from this one and then delete this part. So I would like to see also in your equations why it is like that. Then for the second one again, we copy this one and we drop the x at the end. Again, would like to see why it is like that. Okay, so these should also be fine. I will drop these equations in the Jamboard slide number 4 probably. So at least if you just follow this tutorial very carefully and implement everything correctly, you would get 100 points at least for your course. So, okay, so I added those in the Jamboard. If I run it and see if there's no bugs, then it'd be great. So yeah, so it's cool, it's working. So, just to show you where you need to go, in the Jamboard, see, there is the code listed as well. And in the previous slide, there is the previous code. So, to clarify a little bit more, so here is the y prim, the output of the model. Then we calculate the loss, so that evaluates how good is our model. And then we calculate derivatives, and then we apply the stochastic gradient descent with our learning rate or alpha step. That's it, and we apply it. We do this 200 times. This is with 0.01. Okay, so let's have some basic questions here. So, is it clear so far? Clear so far, and working for you? Plus, minus, and if not, what is not okay? So that's my question in the chat. Meanwhile, while you answer the question, I will quickly code the small plot so you can see how the loss function works. So let me add, well, you don't need to do this. If you want, you can do this. This would be nice. So later we will need to do this always, but in this case I'm just will show you a little bit so how the loss looks like. So, by the way, the thing that we just did is very similar to the homework 2 times ago, so two sessions ago, so you should be able to submit that homework as well if you calculate the equations correctly. So plot, so what about the plot? Do we have the plot or not? So import matplotlib pyplot as plt, plot plt plot, right. So this will be the loss, losses, plt title loss, and plt show. So this will be the way how we train this stuff. So okay, so see, okay, so because we have only 4 data points, this is not like crazy impressive, but still quite nice. So you see that the loss value decreases over the epochs, right? And we can notice multiple things here. So I will go to the Jamboard and amplify them. So I see, I think, 2 pluses that it's working. I would like to see more confirmations that this is working. But let's wait for other people as well. And then we'll move to the next stage, that will be the dataset preparation, and then we'll move to actual proper model. So what I mean here, what is interesting here is, of course, so one thing is the loss is decreasing, of course, by the epochs. And the other thing that you should kind of see that the predicted values gets really like better. So the model is, of course, very weak model. We cannot expect that this model will work perfectly, but still, you see that that this one is a higher value, this is closer to that one, this is closer to this one, and this is closer to this one. I think we could get it even closer if, so it's kind of jumping around here. Okay, maybe so we are initializing it in random. Maybe if we run it multiple times, maybe we could get a little bit better results. So it's fun to see that these curves are every time a little bit different. So here there was a big jump at some point, and now, okay, this looks, so it's not perfect at all, but at least the values are closer. So this one looks again better for other values. Okay, it's really hard. So the model is really weak, very weak model. That's why it's not really converging that good, but still. So the other thing is that I was asking, the question was, why should we initialize the weights as a random variables here? So sorry, I was again not showing the code. So what I did before, while I was not showing the code, I was running the code multiple times, and you see that every time when I run it, we have different conversions of on the loss function, because it's with the random variables. So this is not random, this is random, or initial weight. So initial weights plays a quite insignificant role for many types of models. And in this case, my question is following. So why should we initialize weights random and not just use zeros in as before. So before, for those of you who did the homework 2 sessions ago, we used the sigmoids, and then we initialized with zeros. And as Betty can also testify, her homework was converging really nicely. So with the zeros as well. But why in this case the zeros would not work at all? So do you have any ideas? If you have ideas, please type in why, or minus if you don't have any ideas. So I see Sam answers. So we can teach more and more accurately zeros of the constant. Okay, it's good that you're trying to have some feedback. That is better than not having at all feedback. Okay, so if you look at the equations and think about them, so if you do the forward pass, right? The forward pass now, the forward pass, then there is a multiplication by weight here. So this will, if this is a 0, the output will be also 0 because B is also 0. Everything is 0. That's fine. For sigmoid, it will still work. But for ReLU, if you look here, if this is 0, then there is a 0 coming out of there. And if you look at the backprop is here. I mean, the derivative, it will also be the 0 of derivative. And if the derivative is 0, then it means this equation will not change anything at all. So we will not learn anything. So the idea is that this is called dead neurons. So basically, this is something that happens in the neural networks spontaneously, and there are ways to mitigate it, but it can happen like if you have like billions of neurons, billions of ReLU functions. It might be that, let's say, 20% or 10% or whatever goes into zeros, and then in the minus, and then they are just dead and they are not contributing to the loss at any capacity. So that's why they should not be initialized zeros. If you initialize them by 1, it would work a little better. If you initialize by random, it might work even more better, because then we have some kind of like not really that uniform space of where we start our learning. So that's the reason for that. Okay, so I hope that that's clear so far. It should be clear so far. So then we'll move to the next stage. As I said, it will get we will start combining all of our knowledge into one code. So and then maybe I will test your knowledge on the Python again. So here, let's see. So we will use the California housing dataset. That's why I had the California picture in front of the workshop. So just a second, I will open that one and share the screen to you. So if you don't have installed yet the sklearn library, that you can do with the pip install sklearn or conda. So it like just one line very quickly. So this is a dataset, and maybe I will just add this also to the Jamboard. So this is dataset we're going to start working with, and this is what I mean by that. Okay, great comment. Thank you for the comment that now it's easier to understand the math. So as I say, anything we do is not complicated, but these steps maybe are required for understanding. So here what we have is the input dimensions. So this is 8-dimensional input features. Before we had just 1-dimensional, the number of floors. Now we have also the number of rooms and all sorts of other features. And then we have the target feature that is in the range of like it's probably some, let's say, millions or something like dollars. So you can see like starting from $150,000 till $5 million or something. And we have the samples of dataset. So this is over 20,000 samples. So quite like a reasonable dataset to start working with. So please look at that link that I just gave you, and I will drop this in the Jamboard as well. And later I will also prepare the submission for this code. Okay, I did not copy with my markings. Why it is? So let's try again. Okay, now it is with the markings. Okay, so that's fine. Okay, and maybe I will also drop in a little bit of information what is in those eight factors. So in those 8 factors you can see read more here. Okay, and then we get the eight features. So these 8 features, they're called features basically. So you see there is a median income of the household. Like you can see, like you can imagine if this is like some kind of classified portal with all sorts of like listings of flats and houses. You can see the average rooms, average bedrooms, the position, longitude, latitude, so some of these interesting stuff. So this will be our data set. Again, we have 8 dimensions. Remember, before we had 1 dimension input. Now we will need to project using the linear algebra. So we will have the proper dot products now. So, but before starting working on this, the other thing is that the inputs are not really like very well organized. I mean, they can be in different range of values. So they are not right now normalized. So we will do that first. So we will need to normalize it. So what I propose you to do is that you create a new file. So I will also take a new file, some kind of new file. So California housing regression. Okay, and we will start looking at this code. So import sklearn data sets. I think it was that. Do we need something else? Data sets, yes. So I think it should be enough so far. So then, of course, we also need to import Numpy as MP, and we also probably later will need to import matplotlib, pyplot as plt. So okay, cool. So we have then the data set. So this will be the x and y as the same way as before. So sklearn datasets. Oh, sorry, but it's not here. Interesting. Something missing here. What I'm missing? My autocomplete didn't work. California housing. Maybe I should include that one as well. California housing, maybe. Let's see if I add it with this one. No, this is not what I mean. It should be there. Let's see. Probably my autocomplete is just not working. If I just use the text from the website. Okay, it still doesn't work. Funny. Anyway, let's see. I will start running it and see what is the problem. Okay, it works. So it's my autocomplete is problem. I don't know why it's not giving me the autocomplete. So why? And here we need some parameter. The one parameter that we need is return xy true, like that. And then we can try to look into it. So if I just look in some of the examples, so you know that in Python we can use, in Numpy we can use, and also in Python lists, I think, primarily we would use that in Numpy, but also in Python lists is the syntax of selection. So let's select first 5 samples of X and the first 5 samples of Y, and trying to run them to look what's inside them. So we can see that the price here is 43333, and these indexes are, so and these input features look something like this, where we have 8.3, then we have 0.41, then we have 6.9, and so on. So these values represent, like for example, the we can actually look what exactly they represent. So the third value should represent the average number of rooms. So the third value, kind of interesting that it's not exact number. Maybe they are not in the correct order or whatever. So it's 6.9. Average number of the rooms, average number of the bedrooms. So anyways, maybe they are just like some kind of markers of similar houses, and it's calculated by multiple houses, so it doesn't really matter that much with regards to like exact meaning of those data points. But so far so good. I'm just starting to think that we also could run a little experiments with regards to the Python lists. So, okay, let's do first things first. So, did you got it so far? So, did you got it so far? So, is the code running for you and everything's fine so far? If not, then let me know. I will also drop this in the Jamboard. And then we'll do a small test with regards to the Python knowledge of the lists, and then I will give you a task for this dataset. So nice to see that it seems like that you got along well so far. That is good. That is good. So just a second. We'll try to look up my notes, and okay, before I look up my notes with regards to the arrays, let's ask a question again. So how do you rate your Python knowledge now? So from 1 to 10. So remember, we had this question multiple times. In the very beginning you said you were 8, then you were 6, then you were I think some of you said 2 or 1. So what do you think now of your Python knowledge? And we will do some tests with the lists quickly now. So I will quickly open some file that we could look up. So please let me know what you think of your Python knowledge so far. And okay, so I mean, yeah, I don't want to make you feel that bad, but this was just objectively, you know, like the more you know about some of the stuff, the more you know what you don't know. By the way, we have quite a lot of interesting stuff that I could test you on. Do we have anyone who is confident that he knows Python very well at this stage? And remember that what we do now is it's kind of useful for learning as well. Okay, so I see that nobody is very confident right now. So the humble and not pride people, that is a good start for great success. When you have a lot of pride, then it's like a just precursor before the downfall. So that usually happens in the history. So the humbleness is really good one. So here, let's say we have 1, 2, 3. So we have some array, very simple array. So let's start by some very simple questions, okay? So what will be the output? Again, please don't do the monkey typing and trying to type all of my experiments yourself very quickly. Just give me answer, please. So if I use something like selectors like this, so let's say this will be 1, and if I select then -1 and -2, so what will be the output of this print line? So what do you think? Again, please don't do the monkey typing. So I know if somebody can type very fast and test with my questions, that you can do, but it's more fun if you just think of what the code will do and answer. So, and if you're not familiar with this syntax, then please type in minus. So I have some interesting answers so far. So, but if you're not familiar with the syntax, then also please type in some like don't know or just minus. So that would be helpful. Then I understand what to tell more, because we will work with these kind of syntax quite a lot. Okay, so I have three answers so far. What others think? Very interesting answers. Okay, I hope that. So by the way, we have only 4 outputs here, but okay, but maybe it was intentional for Emils to write it like that. Okay, so that's really interesting feedback. I was not expecting that much. Okay, someone reminded me of syntax, right? So that's great. That's great that Kristaps understood the syntax. So yeah, that is really nice. So the Gint's also one of the ones who is leading the pack here as well is giving some good answer. So if I run it, that is the correct answer as for the Kristaps and Gint's. So that in the Python we have this very nice syntax of using the minus sign for the selection of the values of the array, and we can select elements from both sides of the array. We can start selecting from this side or from the back of the side. So -1 would be then the 3, then -2 will be 2, and then this is from this side. So very, very useful syntax. Highly recommended. So that is one small test now. So let's see more tests. So print. So let's see what we could do more. So let's see. So array of, if we select something, so let's see, 1 till 2, and so like this. And if we select, let's say, then something like array, like let's say, so this was like that. So I think, let's see, this one. Maybe I myself let's see, but so the second index should be so I think we can do this actually. So let's do this, and let's do then hopefully my own syntax is okay. So anyway, and then we can select something, let's say -2 like this. So what do you think what's going to be output here? So and also if you're not familiar with this syntax, then please let me know what it means. The minus syntax is very, very important, by the way. So you use it quite often. So anyway, you will see it later. So what will be output here? Okay, I see at least 2 answers, right? 3 answers. Okay. Right. So I will try to explain also a little bit. I think at least some of you got it right. If hopefully it's not monkey typing trying to test it, but at least some of you got it right. So I mean, the syntax is following. So you can have array and you then have begin index and end index not included. I mean, like yeah, +1 or the next one, right? So you have this kind of syntax for selecting any range of the array, and you also can do this backwards, right? So you can select from a minus index to some other minus index, so from the other side of the array, and if I run it, basically, so you will see that this is a 2 last elements. So -2 just means basically I will select anything from the end till -2, so those last 2 elements. And also must emphasize that if you don't enter these values here, it will just automatically enter 0 there. So if I don't enter value, it will be exactly the same as this. And also the syntax is true for the other way around. So if I don't enter value here, then this means, so from the begin index, so this means then the last index automatically. So this would be just a len of array here. So like that. So I hopefully this is understandable so far. By the way, let's check it. Is it understandable? So, do you understand it well? Understand it? Okay. Plus, minus. By the way, these. So I see that you're not very happy about the Python, but these kind of selections can be done in multiple dimensions as well. So you can imagine if you have like square of dimensions and you want to select just one part of that square, so that you can do also using this kind of syntax. Maybe I should even show you that. So do you understand this so far, plus minus? And I probably will show also some examples with those multi-dimensional selections, otherwise you might be confused later. But before we do that, we'll do a couple of other small experiments. So nice that you're following up on this. That's good, plus plus. Hopefully that's clear. Okay, let's start with simpler experiments. So okay, let's don't complicate things, make them very simple. So let's see, if we try to run something like this, what will be the output of this? So we will have four lines. So what will be in those 4 lines? Okay, I see that it's counterintuitive about the end index. I kind of agree, probably, but you get used to it. But what do you think about the outputs for this small task? Any ideas? By the way, if okay, I see at least one answer already. That's great, and I like that Kristaps is not monkey typing on this answer, so that's great. Okay, I see quite a few answers now. Out of bounds, with every iteration, the first element will be removed from the output. That's fun. And the last one will be empty array. So the GINS probably is the closest one to the answer. So that is really also kind of, let's say, fun or interesting feature. So if I run it, you see that the output is that the first will select from 0 till end, second select from 1 till end, third select from the last one, and then when we run over the index, right, we get just the empty array. So I'm not getting the syntax for within the print function. Interesting. So if you Armans could write like just like that part which you're not getting. So the print function is overloaded function where you can enter whatever arguments you want. And so so the first one is just the counter, and the second one is the output. By the way, I probably should just delete the counter so that you could just answer those answers. But anyways, so this will be this one. Okay, so we got the empty list at the end. So let's change a task again. Okay, so I don't want to just delete those things, so you can think about them later. So let's keep copying them. So now, so ignore the first argument, but we'll look at only this one. So what will be output now if I'm deleting the colon there? So what will be the output now? By the way, what we do right now, it's kind of also important in the sense of we will start working with those linear algebra things, and also with a data set. So it's kind of important to follow up on those things. So we have one idea from GINS. What about others? Yeah, so you got this one right. So you got this one right. This is correct. So let's look at the next one. So I mean, of course, if we just select non-existing element, it will give an error. But keep in mind that previously, when we selected the third element with the range, it worked. There was no error. So you can already imagine how you can use it in different ways. So let's look at some other way. So let's see if we type in like this. So what will be output now? Probably if you already typed the code, then you just run it. But it's more fun to try to think about it a little bit and answer the question. By the way, again, my my stuff is missing up here. Just a second, sorry, making the task very complicated. So now it's clear. We have the array value of this. So any ideas? Okay, I like Kristaps is giving some answer. So this will be selection, so that this will first selection will go from nothing to nothing, and he says that this will be 1. Then the second section will go from nothing till 1. Interesting answers now coming in. So remember that we're starting from 0, and also the I is starting from 0. So that's interesting question, the interesting answers. So if I rewrite this equation like this, maybe that makes a little bit more sense. So Kristaps is correcting his answer, and I think now you're getting that this is actually the true answer, as also Ginz is reporting. That if we do this, we see that the first will be empty array, then there will be the 1, then the second one is selected, and so on. So okay, that one is fine. So now let's do another experiment. So what about if I use like that? So what will be answered now? With array of minus e. We have one idea. By the way, this question is kind of trick question, but at the same time interesting question. So if you think about it arithmetically a little bit, you will understand it. So okay, so the Ginz is saying something, but basically why it is like that. So if you think about arithmetically what it is actually, so if I run it now, let's see. So the first one is 1, then there is a 3, 2, 1. So but why it is like that is because if you think about it, so e minus 0, so if I write it like, so this will be minus 0, so it doesn't, so this is basically the same as just a 0. So you can think that basically the first run is just a 0, then the next one is minus 1, then the next one is exactly. So Ginz is giving also the same thing that I'm just right now saying, that that the minus sign in front of 0 doesn't make it any minusy than 0. So that's why it works like that. So, and then let's do the last experiment. So what happens if we do following? So I'm happy that that I got you a little bit, and you yourself also understood how it worked. So that's great. That's great. Hopefully, also then this question is much easier for you, and you will just give the answer correctly. So I see some answers coming in. So if you think about it again, so like the Gins is giving some kind of good explanation, I guess. So that if you think about it again, that means that 0 is 0, right? So that means array 0 till end. Then the next one is array -1 from end. So that means that we will select everything from end up to -1. That's the last element, right? So then the next one will be minus 2. Then the next one will be -3, right? And if I run it, I will see that it works like that. And so again, kind of, if you think about it a little bit, so like the minus sign will give that 0, and basically that's 0, and then it works in a different way. So if you write the code, it's very easy to mess everything up if you don't have some kind of checks on those I values. For example, you go from minus from back, and then like maybe there's no elements and there's just 0, and then you just return everything. So very easy to mess it up. Anyways, so before just returning to the deep learning models, let me show you quickly additional syntax. So this syntax probably I will drop also inside the Jamboard just for those to follow up. So let's say we have a two-dimensional array, so array two-dimensional, 2D, and we'll do the import numpy. So this will not be a question, it will be just like it will be just the example, so to show you how to use correctly this syntax. And we will use the zeros. So MP0 is very nice function. You can initialize arrays of specific shape. Let's say we have 10 by 10 array. So, and then the next thing what I will do is I will add some kind of print here, whatever, and add the breakpoint. So the PyTorch, if you use this environment, It's very nice that you can debug it very nicely. So let me show you. So if I use the VeA array, I see my array here as all of the zeros nicely, right? And what I would like to do is select some small square here, and to select the square here, I will use the array selection syntax. So let me show you. So for example, if I want to select some square, let me see. So so first let's look at the rows. So this will be the y-axis. So from the y-axis, let's say the square will be from 1 to 3, and then in the x-axis it will be from 2 to 4. So this will be 2, 4, right? Okay, like that, and we will select this and we will give the value as 1. So be careful to see here that I use the comma in here. So because we have now two-dimensional array, we can use comma here. So we can also use the syntax similar to following, like we can select, let's say, the first row, and then select the first element, like the second element in that row. We can do also in this way, but in this way we don't have the property of selecting like even regions in the array or the matrix. So here, if I run it again with this syntax, and then if I look with this one, you see very nicely there is this segment selected by this syntax. And again, you can use the minus signs here. You can use the not filled information, like just leave with one of those like colons here, and so on. So hopefully that is clear. And you can have many dimensions. It's not just 2 dimensions. You're going to have 3 dimensions, 4 dimensions, 5 dimensions, and in deep learning you actually do that quite often. So is this clear with is this syntax clear? Is this syntax clear? Plus, minus, and if something not clear, then please ask what exactly is not clear. And if it is clear, then please remember it and use it and try to understand it better, because this is something you will need to use quite often in this course. Okay, great. It seems like that you're getting it. So now let's return back to our code of the California housing dataset. I will add as a homework for you probably to normalize the data. Now the data is not in the range from -1 to 1 or 0 to 1. It's some kind of not defined range. But so we will just add for the later to do later normalize x and y, so that it would be, so let's say it could be, let's say -1 to 1 or 0 to 1, whatever. So that we'll do later. We'll not do this now. So now, because of the constraints of the time, let's keep coding up all of our knowledge in one place. We will start combining all of our knowledge with regards to the object-oriented programming. So the first thing with regards to the object-oriented programming, that's why we actually learned about this, is because we need some kind of class that will hold our variables, and each variable will contain not only so there will be init. It will not contain only the value. So the value will be something that we will define, of course. So there will be value, and this is object probably. So we will have value. For example, what is value is that like the floors of the house, or the weight value, or the bias value. This is our value for each of the instances that we'll have. We'll also have the gradient for each of the variables. So gradient, grad. So this will be initially like NP like zeros, like value, like that. So the idea is that we want one like class that will hold us both sides of the coin. So we don't want to always recalculate our values. We want to calculate values once and then use them in function graph independently many times. That's why we have just this one holder of our values. So that is one thing that we're going to use. Then, of course, we have the most common part of our neural networks is the linear layer. So class linear layer. So this will be that linear function that we just made before by hand by using all of those equations. But now it will be a class because we want to replicate this many times and don't calculate the equation again. So here we'll have again some very specific things. One is that we'll have the constructor, and the constructor will get two inputs. So one is in features and the other will be out features. So the in features and out features in this case means following. So here we have x of, so the x is shape is the n number of samples by the 8 features. That will be in features in the very beginning will be 8 in features, and then the y here we have the n comma 1. By the way, it's not like that, we need to expand it, so let's do that as well. Y and p, so expand dims, because in general, because it's initially actually, so I will show you x is 1. So before this operation, the y is actually in the shape like that. But the neural networks with regards to the mini batch would never work with this kind of shape. We always need to have the features as the last dimension. That's why we have here 8 dimensions of the input features and 1 dimension of output feature. So just to double check, so you're following up on this point, is what is the y here? So in this case, like just like in human terms, what we actually have in that variable y. So at this point, it's actually not variable; it's just a data array, but we will convert it to variable very soon. Okay, funny answer, vector. Okay, so it is probably, it is a vector in some sense. So, but what data is inside x and y? So I just want to make sure that you understand that we are not working with some kind of abstract stuff. So it kind of helps to understand a little bit the task. So this will be actually integer. So if I add this notation, it kind of informs the Python interpreter that this will be an integer variable. So my question is, so by the way, if you don't know the answer, then type in minus. So what will be inside, what is inside x and y, or type in minus if you don't understand what is inside those two variables, or the, let's say, arrays. By the way, the things that we right now constructing, they will be super similar to the PyTorch itself. So now we will kind of implement the PyTorch things ourselves. So I see that Armand is giving correct answer. So the X is all of those features of the house, the floors, rooms, bedrooms, whatever. So and what is Y? That's a funny answer. The Y is target, what we want to understand better. So the target, what is target? Do you have ideas in human terms? So Y is all the samples? Not really. So we have our samples is combination between each pair of X and Y. So each sample, so let's say sample 1 is the X0 where we have 8 dimensions, so there's actually from 0 to 8 dimensions, and plus also Y0, and here we have 1 dimension only. So this is our sample 1, this is our sample 2, and so on. So the sample 2 is with a selection of 1 here, the sample 3 is this combination. House values, good answer. I mean, the house values is the price. So in general, yeah, you're right. So Y is the price. So Y is price. So that's good. So here, if we think about the linear layer now, the linear layer in features will be 8 features of the inputs, and out feature will be 1 feature. So this 1 feature will be the price. And the idea here is following, that we want to make this function in a way that we will use the dot product and matrix multiplication using dot product to project the 8 dimensions to 1 dimension using learnable weight matrix or rotation matrix. So we just project it on some other plane, and we use it by the same equation as we did it all the time already. So let's do that then. So we will have the weight variable here. So we will just initialize it once for every linear layer. By the way, now, as you see, we will add our variables inside our objects. So we don't need to make them so to pass to each function many times like we did before. Remember W1, W2, now we have just W encoded inside the class. So embed, actually it's called encapsulated. So here we have the W encapsulated value, NP random, and this will be just a normal distribution random. I think random was normal or uniform, don't remember, doesn't matter actually. So then we'll have the out features by in features. Again, the fun thing is that this matrix that we're now constructing, we're constructing a matrix here, right? And giving the value there. This is something that it doesn't matter that much if this is in features and out features, because depending on the calculations, you can always transpose it, right? You know that operation transpose. So self B, it is then the variable. And this will be the bias, and this bias will not be matrix, this will be just a vector. And let's kind of ask you some questions. So this will be a zeros. Normally biases are zeros. And what should be the shape here? So let's ask some question regarding this. So what should be bias shape here. So what or minus. If you don't get it at all, then type in minus, and meanwhile I will give you some hint. So the out will be following. There will be weight c dot the dot product with x plus b. So if you remember robot arm, if you remember asteroids, if you remember linear algebra, this should be very trivial question. So what should be the shape of b here? By the way, to not confuse you, let's say that this will be probably transposed, but actually no, it should not be transposed, I think. So yeah, it should be fine like that. Maybe the x should be then transposed. So the matrix multiplication is tricky because sometimes you need to transpose things. So maybe that, but still, it doesn't change that much the question if you give me some answer. So the shape Gint is saying the same as y, and Armand is also giving something like that. Do you have any other ideas? So if you think about this in 2 dimensions, so maybe another hint. So if we think about this in the 2 dimensions, so that would be that in features is 2 dimensions. So in features would be 2D, and out would features would also be 2D. So if this is the case of the, let's say, robot arm, then what will be the bias there? Because in robot arm you already did this, remember? You had rotation c dot of the let's say what is position vector in 2D plus transpose vector, remember? That was what is in the robot arm. So what was the shape in the robot arm for the t here to make this equation work? Because if you don't have correct shape, this equation would not work at all. So, and this is the same analogy here. What will be the shape of b for this equation to work? So if you had, like in robot arm, where you had rotation of 2 dimensions by 2 dimensions, and then you multiplied, have the dot product by 2-dimensional vector, and then you added something here. What was the dimension of that t vector, translation vector? So still, I don't see any correct answer. If you can have the answer or type in minus, we can move on. Do you have any ideas or no ideas? If you have no ideas, then type in minus. But if you look on your code that you did with the robot arm, it should be very obvious what is the shape for that B or T. So that's okay. So I have quite a few minuses. That's a little bit sad, but let's see. So so in the robot arm example, you had some new position. So you get a new position by rotation matrix that have the shape of, the rotation matrix shape is 2 by 2, and then you do the c dot, so np dot or whatever, dot with rotation by the position. So the position shape is, in this case, shape is 2, and after this operation, with regards to dot product that you also had to implement by hand, that I assume that those of you who type in minus did not do this, and you will have to do this at some point, and if you leave it to the last moment, it will be difficult. So you get out two-dimensional vector, and the only possible way that you can plus it here, the two-dimensional vector, you cannot plus it with 2x2 matrix. So that would be, again, the translation vector should be also in 2 dimensions. So translation shape is again with the 2 dimensions, and then it works. So if this is analogy here, that means that the B output is something at the end that before the output. So that means that this will be out features like that. So this is if you see how the dot product works, that we covered like at least 4 or 5 times. So you should look at those equations. So this is like summation and multiplication and summation, the rows by columns, and in that way you project to some different dimension. So here basically in our case it's similar like this one, but the only difference is that let's rewrite it in our case. In our case it looks something like this, that our rotation matrix looks like 8 to 1. Then the position coming in is 8, then the dot product output is then a 1, and then the T shape is 1 because that's our out position. So hopefully it makes sense now. So let me ask you, does it make sense now? So plus, minus. Should we talk about this even more, or do you get it now? By the way, the output dimension can be anything, you know. Like if this is a hidden state, maybe we want output dimension to be 4, for example. Then in this case, this will be also 4, and then the T again will be 4, for example, if this is a hidden state. So I have 1 plus, 2 plus. So this is a dot product, yeah, scalarais matrix reizinājums. So this is something that we did a lot with the asteroid game. So if you did not complete the homework for asteroid game, then you should do this very quickly, because it will be very hard for you later then. So we have 2 pluses, that's great. What about others? Okay, hopefully it makes sense. And so for the homework, I will definitely give you the normalization of the vectors. We will not complete everything today, but at least we'll be quite close to proper deep learning model. So then the next thing that we'll having here will be the so the syntax was mixed up, so I'm not. Again, I'd highly advise, I see those people saying the minuses, I highly advise that you do the homeworks, because those who do the homeworks, like for example Gintz is saying the plus, and I see that he also did the homeworks correctly so far, like most of them. So I mean that could help definitely. So then let's see, we have the x, and this will define as none. So this will be something that we will maybe also, let's give it the type name there. So this syntax will just help autocomplete. But the idea is that I want to store the x as well in our like this this object. So I want to store it because I don't want to recalculate it when I do the forward pass. So we will have the forward pass and backward pass. We will go with a function in the normal way, and we will do the back propagation with gradients in opposite way. So we'll have two directions, so I don't want to recalculate it. So we'll use this one, then we'll have the forward pass. And the forward pass input will be x, and this will be variable as well. By the way, I probably need to add those because I have seen students not understanding what is coming in these inputs. So this is not Numpy data coming in, this is our own data coming in, variable. So there is a variable, so then we set the x of the x that came in. So we want to remember what was the x that we just saw. So that is one. And then we want also to calculate the output. So the calculation of the output is really trivial. That is what we did many times already in this course. So this will be the NP mat mul. So mat mul difference from dot product is from NP dot is that we will have the mini batch or the batch of many samples repeated this dot product for every sample in the batch, not just like one by one sample. So here we have this self W value because the value contains our matrix there. And we will then do this one with the x value, and we will need to transpose it. So the value, okay, I forgot to add also here a typo. NP ND array, I think it was ND array. So I mean not typo, it's just like type definition. So if I add those, it's easier for me to code then. So if I write then here, there is a transpose, so I transpose it. Then I also need to transpose this whole matrix, because now after the matrix calculation it is like a stack, not a, so it's a horizontal, not a stack. So I want it to be a stack, that's why I just transpose it. So the transpose operations, you know, should not be scared of them. They're just like if you have a vector in a horizontal position, you want them in a vertical position. This is like very trivial stuff. So self b value. So this one we also add. Okay, and now we have this one ready, and we will return self output. And here the tricky part starts coming up. When we will chain, we have linear layer inside another linear layer, inside another linear layer, inside another linear layer. This output will become very important, because the output of one function will be the input of another function, and we will need to multiply that gradient for the chain rule. That is something very important. You kind of need to understand it, that this output will be input for next function in model. And because if you remember that knowledge, we will use that in the backward pass. So then we have the backward pass, backward. So the backward pass is the calculation of the derivatives. And derivatives we already know how to calculate. They are really easy because we already did this so many times. So now here self b, so derivative with regards to the for this function with regards to the b is 1. Remember, because so if we have, so what I mean by this is so we have the function. Maybe I should write it. No, I'm just hating writing so many times already. I don't want to write it again. So just x plus b, and if I do with derivative with regards to the b, right? Derivative with regards to b. So the first part is just like 0 because that is a constant, and then we have plus b in squared of 1 minus 1, and that is the end is 1, right? And that's why the gradient here is 1. So that is cool, so far cool. But then I highly told you that here this output might be the input for next function. It might be and it might not be, but if it is, so actually the output of the next function, let me think, I think in most cases it will be the output for the next function, except if this is the last function. So then we multiply this by the chain rule, so we use out grad. And here you see the beautifulness of this code, because now we have the connection of the function graph. So if we call these functions in a stack one by one, it automatically connects them together by the derivatives using these multiplications of the previous function outputs. So this is one thing already done, so that's great. Then we need another gradient. So the another gradient, of course, so maybe I should write it down a little bit. So this is dB, dB is 1 times the chain rule of previous function, right? And if we are at like the very beginning, I guess, should it was a beginning, or so this is a beginning. So if we're at very end, then we don't care about the last that chain rule. So here, let's see, we have the weight gradient. And in this case, again, so what was the chain rule here? If we, I mean, not the chain rule, but what was the gradient here with regards to the V, the W, the gradient is X, of course, that we did already. And again, we have the multiplication by the chain rule. But in this case, this is not some scalar value that we can multiply it with like that. This is a vector. And to multiply vectors, again, we need a dot product. So we do the dot product. So it's a NP mat mul. And here, again, we have a problem because the X is a vector and the chain rule output is also a vector, but this is a matrix. And we need to somehow multiply them like one vector turning on side, another one like one is vertical and one is horizontal, and that's something that we can easily do by expanding dimensions. So we can make one vertical and one horizontal in this method, but there might be also some other methods. So we can expand dimensions of self out grad. By the way, again, the order here is dependent on the transpose. So in this case, we can leave it order as this, but if you want, you can change it. So here we'll have this one, and also because they are vectors, the order is not that important here. So if there would be matrix multiplication by vector, then you must be really careful. Okay, so like that. That is great. So we have this one ready. And then we need the last bit, that is the derivative with regards to the X itself, because again, this linear layer can be, there can be many linear layers. So this will be self X grad is the NP mat mul of, so this will be then, so let's see, what was the, so it's easy, basically the X is W, so in this case, and in this case, again, of course, multiplication by the chain rule. Chain rule, actually the chain rule is not the function, but the D of function, of course, derivative, right? So that's why we are multiplying the grad there, like that, and here we have the actual proper matrix. So the W is matrix actually. So the W is matrix, and in this case that is a matrix. And let me think. Okay, but the problem is that the output is now in a different dimension that was here. So now we need to transpose even this guy. So the output is now it's not like in this forward pass where we had the int features, and this is also int features, but we need now to have as a first dimension the out features. So we need to transpose this one, and we also need to transpose the out vector, because that is not horizontal here. So self out grad transpose as well. So that's great. And at the end, we will actually use this. So now it will be horizontal, and we will need this vertical. So we'll use the transpose again. So now this is also ready. So basically now we just implemented the linear layer, and I will quickly do some test code at the end, and I will add this to the Jamboard as well, so you can follow up on this. So don't want to scroll too fast, sorry for that. I will scroll a little bit up and copy part of this code to the Jamboard. So this part of the code is going into Jamboard in the 7th slide. And by the way, this syntax that we do so far, it is like almost one-to-one that you get in the PyTorch. So that is very important. We are coding this stuff by hand, and at the same time learning actually how the like state-of-the-art machine learning libraries work. So we added those in the Jamboard, and now I will make a dummy code just to make sure that everything works. So let's see. So we will have the linear 1. So this will be linear function 1. So this will hold the in features will be 8, then out features will be, let's say, 4, and then we'll have the linear layer 2. So this will convert to 4 to 1, because if we just test with 1, this is really an exceptional case where we have a one-dimensional stuff that works many times even when they should not work. So we'll have this thing ready, so that's great. So then we have the x thing. So x, we can have the variable, and the value could be actually something that we select out of our x, the data set. So if we select of the data set first 10 samples, so first 10 samples of the data set as our x, and then we call some out here of the linear 1 forward of the x, and then the y prim would be the, so by the way, multiple linear functions in a row doesn't make sense, but in this case I will do that just for the time constraints. So like that, and then let us think what will happen. The grad will be 0, it doesn't matter, it's basically, hopefully it will just work. Hopefully it will just work. Let's see if I call linear 2 backward and then linear 1 backward. Hopefully this code will work, so I will just test it, run it. Okay, it works. So, except, is it the same code? Yeah, it is the same code, yeah, so it works. So I also add some test code that you can play around and think about it a little bit till the next week. And I will have the homework for the normalization of the dataset, so that task should be quite easily understandable. So it's the idea that you need to make sure that each feature of the x is in a range from -1 to 1, and the output is also in the range from -1 to 1, and then we can, if we know the original range, we can go back to that original range. And if we don't scale these inputs and outputs, the model will work a lot worse than it could work, because they are arbitrary just numbers. But if we scale them, they work better. So we will talk about this later as well, but that will be a small homework. So yeah, you should get this one working. Basically, we have 8 integers, then we have some hidden layer. Normally what you want here is in between here a relu, so that then it would be properly what we had before. Maybe I should actually add this as a homework, but I think about it. I just don't want to make it too complicated. I think we need to work with this a little bit more ourselves, and then we can do this as a homework. So there will be a ReLU in between, like that. And then at the end, of course, before the calling backward on nothing, on zeros, we will actually have the loss function here, and then we'll have the loss backward. Hopefully it makes sense. I really hope that the idea how this should work makes sense and how this is constructed, but next week we will dig this a little bit deeper, and my plan is that by the end of next week's first tutorial we will have it running properly as a small deep neural network, I mean not shallow neural network, and on the Wednesday even, I mean on a Thursday even, we could start working with PyTorch as well. So that will be quite fun. We will go from Numpy to PyTorch and back multiple times so you can understand better the mathematics behind it. Okay, so that's it from me today. I will add the homework. Please do not delay on your homeworks. The more you delay on your homeworks, the harder it will be for you at the end. Like I see that some of guys like Gins and VeA is doing really great. Some are just lagging behind, and we already see the effects. If you don't do the homeworks, I ask the question, and then you say minus, you don't understand because you never tried it yourself. So please do the homeworks. Okay, so we'll meet next week. Bye bye.